Hey everybody, this is Jeff from Robotics. In my last video, I made a simple linear actuator with a DC motor and 2 gears. Today, I'm redesigning the actuator and making a few improvements. The case hasn't changed a whole lot. I've redid where the end stop meets, and I've redesigned this just slightly so that it fits a little bit better. We have a through hole here. I put that in there so that I could put in another end stop. I'm thinking a Hall effect sensor to detect when the drive runs out. That way it'll still stop before the output shaft hits the main drive gear. Here I've added the planetary gear case, and that's basically similar design to the first section of the case here, just an extension of it with, of course, some gearing on there so that the planetary gears have something to turn on. And then, of course, we have the final part of the case here, and I've modified this from the last version to accommodate an encoder here and 2 reduction gears that will drive the encoder. I tried it without the first reduction, but the encoder tends to skip when it goes too fast. Here is our rotary encoder output, and here is our rotary encoder reduction. We see that the output shaft here connects to the first reduction, and then the first reduction goes to the encoder input. So adding that back on there, we have our spot for our rotary encoder. And we have a nose cone, and that looks something like that. I'm calling this version 2, so let's get it together and get it tested. We have for the A case, our first stage gear, our intermediary stage, which holds the planetary gear stuff, planetary carrier set, the 3 planetary gears, the output. This will be the B case, 2 reduction gears here, a 5/16 thread rod, DC 570 motor, a rotary encoder, and an end stop. 2 bearings, 1 5/16 nut, 4 M4 socket head cap screws, 3 M4 nuts, 2 M4 screws, 4 M4 2-inch machine screws, 4 M4 lock nuts, and 1 wood screw. Our nose cone, and of course we have our cover with the wires already installed into it. You can see that inside of our planetary gears I have a little piece of nylon. I just used this type of tubing for that, and I simply pushed it into the gears and cut it off. You're also going to need a little extra wire, of course, to wire up the encoders and the end stop. The first thing I'm going to do is put in the bearings. Put in this nut. We're actually going to need one more bearing to put in here. I'm going to take the motor, that ought to be good. Next we're going to install these nuts in here. These can be kind of a tight fit, so sometimes I use pliers and just squeeze them down really nice. Since sometimes these will rattle out, what I like to do is use a bit of blue thread lock. Drop a little bit. Alright, now we can take the planetary stage, add some more lithium grease to that. Shove that in there. And give it a nice turn, make sure it's all spread out right. So this one here is a pretty tight fit, so I'm going to put that one in first. Yeah, make sure that seats down in there nice. Okay. I'm going to put this on. Add just a little more lithium grease. Okay. Next, we're going to add the reduction gear for the encoder. That just goes in there with your other M4 screw. We have to line up the encoder with the flat part here. And we're just going to line it up there. There we go. And it's in. Now I can put on the nose. Alright, for the end stop, that'll just sit in there and you can just hold that in with a little bit of glue. Okay, so I'm going to put a little bit of lithium grease down in here, just squeeze it. Okay, last stage is the wiring. Looks like I'm going to have to clip these screws off. There we go. Now it fits. All right. So out comes the test rig again, and as you can see, I've made a couple of changes to it. I've made the wiring a little bit more versatile for other things. I've mounted an Arduino Mega here. I have two of the BTS 7960 drivers here. My pot, my end stop buttons, and of course the physical rig. I've also added a power supply that's mobile back here. You can kind of see that, along with some breakouts and a switch. I've also added a bit of perf board that I can add breakouts wherever I need to. This is definitely going to be an ongoing development, so I kind of just change it around every time I have something new I need. But having a little test rig like this is relatively handy, especially if you do a lot of prototyping. This is the code that I'm using. At the very beginning, I'm just defining everything, and I've got my PWMs, and these are the definitions for the encoder. These are the end stops here, and this here is the pot control, which is basically the speed control. I've set just an arbitrary threshold which determines whether or not it's going forward or backward. Our button states, of course, and just the value that the pot reads out. In our setup, I'm just defining the inputs and the outputs, everything here. And of course I have our serial terminal here. The first thing I'm doing is changing the values of the pot from the 0 to 1023 to negative 255 to 255. So I'm setting the clock inputs here for the encoder so that the encoder can count. I get the encoder started, and that will print out on the serial terminal which direction and the speed. And then down here is the motor control. So if you have the value higher than the threshold, it'll go clockwise, and if you have the value lower than the threshold, it'll go counterclockwise. The buttons here are for the end stops, and as you can see, the in button state, I just labeled them in and out. It doesn't really make a big difference, but I assume that in would be withdrawing the actuator, and then the out would be reaching the actuator out of the case. So of course, if it's going one way, it doesn't need the other end stop to work, even if that's on. In fact, if this was activated, then the only direction it could possibly go would be this, and vice versa. So if this is triggered, then it could only go the opposite direction to move away from the end stops. And then the last bit of it here is just if nothing is happening, then the motors are both off. And then I just have a 10-second delay. So a lot of you have reached out and asked for the CAD and Code. I'll go ahead and publish this on my GitHub so you guys can check it out. Feel free to modify it and add some more features to it if you like. But this is pretty comprehensive for at least what I've been doing. Let's get this mounted here. Let's look at our motor output here. Well, we can see that the encoder keeps relatively good track of the position, so we can definitely use that in a formula to find out how far out the actuation arm is. This is what I'm using for my weight testing. My test rig is right here. I've taken the actuator off, and then I just got this suspended with some wire, and I'm going to add weights accordingly. We'll see how much weight this can hold, and we'll find out. Here is test 1 at 2.5 pounds. At 5 pounds. At 7.5 pounds. We're at 10 pounds. At 12.5 pounds. 15 pounds. I gotta admit, I'm kind of nervous on this. This is 17.5. All right, this is 20 pounds. I'd say this is a big improvement over my earlier version. It's definitely stronger and more reliable than the last one. Next time, I'll be doing some much more practical testing when I use them in a bigger project. I hope you've enjoyed watching this video. Please let me know your thoughts and suggestions in the comments, and please consider subscribing to show your support. Thanks for watching. See you next time.